Okay, folks, this will be Chapter 1 lecture. Now, what you should be doing for studying for this course is every time I'll be releasing these different chapter lectures. I should be releasing one every week. This second week of courses, I'll be releasing two to catch up because I've been having some issues. There's lots of things going on right now. It's kind of crazy. Anyways, and during these lectures, I'm going to talk about this. I'll show you some examples. Uh, One of the things you want to pay attention to here is all of the stuff you need for doing the homeworks and doing the exams is going to come from these lectures and these PowerPoints I give you. Okay? Now, I will tend to spend more time on math problems, and that's simply because it's not because most of the questions in the exams and homeworks are math problems. They aren't. Actually, the number of math problems, the worst exam I've ever given in this course for a number of math problems was 1 in 5 of the problems was a math problem, which means you literally could get a B and fail every math problem. Just because this course is not particularly designed to heavily test your math. What it is designed to do is give you basic concepts you can use for sciences and chemistry. It's designed to give you basic problem solving skills you can use when you encounter a science or math or a chemistry problem. Now, one of the things I would like to point out is everything around you is actually based on chemistry and science. So I find it a little bit frustrating that Americans and really people in modern world do not know more about sciences, considering that they oftentimes get sold false bills of goods, right? They get sold bullshit. And they don't know it's bullshit because they don't know any chemistry or science. So hopefully that will help you out so that you can actually sieve through the crap you get told. Uh, if I was to be very frank and honest with you, about 50% of what you get told on the news programs, if you watch news on TV, and about 70% of what you're getting told when if you get your news from things like Facebook, is just outright bullshit. Completely wrong. They don't know what they're talking about, period. Okay? It's bad. The world is incredibly drowned in misinformation these days. And one of the things that can help you is if you have these basic concepts down, you can sift through that bullshit. And it can help tremendously. All right, so chapter 1, this is just going to be an overview about chemistry. Really, you're going to recognize the first few chapters are according to the national standards that the middle schools are supposed to be teaching you. You should have actually learned most of this stuff in middle school. However, according to the national standards of high school, what you should be taught by the time you get out of high school, you really should have had like the first 4 or 5 chapters down. However, I have found that there's probably a good 1/3 of my students every year, or up to sometimes 1/2 of my students, that have not been taught this. And that's a shame, but it is what it is. So, yes. One of the things about chemistry you gotta keep in mind is when you are looking at this chemistry and learning chemistry information, it's all going to build upon itself because really we're doing several different things. Number one, we need to make a new language that both me and you can communicate in. And this is the language of science and chemistry. And this language is much more exact. It doesn't have things like a lot, a little. It has very specific terms so we can communicate in concrete, specific terms and reduce that amount of miscommunication you would normally have. Now, if you don't bother learning any of this language, you're just simply not going to be able to do it. You won't be able to communicate in exact terms. Now, you will also notice when I do these lectures, I tend to give you some meta knowledge, as it were. It's not the exact subject matter, but it is how to learn and better utilize what you learn in the subject matter. So, for example, one of the meta knowledge things I typically bring up in one of my first lectures is uh, think about what you should be learning and getting from a college degree. And so, most people think it's the knowledge that you're supposed to be getting. So, if you're a chemistry major, you would be learning chemistry facts. And that's what they think the important part of taking these courses is. Or if you're an art major, you're learning facts and techniques for doing art, right? But that's not really true. That's actually probably only the third or fourth most important thing about a college degree. The most important thing about a college degree is you learn how to rapidly study and then deploy knowledge. Literally, all those times that you're cramming for exams and you're trying to rapidly learn material over a course of like a couple weeks, that's the most important thing we're teaching you is how on Friday to get told, hey, Monday you need to come in here and be able to do this skill. And then you study over the weekend, you come in Monday, you perform the skill for your job, bam, you did it right. That's what you're learning from. That's number one skill set that people want from a college degree. The second skill set that you want from a college degree, specifically that you're going to help yourself build here in your science course, is critical thinking skills. Now, uh, I know that a lot of you may have, before I talked about this, thought that critical thinking had something to do with thinking outside of the box. That's incredibly not right. Okay? So, thinking outside of the box is called lateral thinking. It's literally thinking laterally, right? Moving, so you see a mountain per se, instead of going over the mountain, you figure out, hey, it would be easier just to go around the mountain. So you go around the mountain. There you go. That would be lateral thinking. Critical thinking is almost the opposite of that. So it's almost opposite of thinking outside the box. It's seeing the box, dissecting what the box is made out of. Is it actually a box? Is it a cardboard box? Is it made out of something else? Why is the box there? What is the uses for the box? Why would somebody make that box and then tell you to be in it? Okay, that would be critical thinking. Or in the case of the mountain example, you would see a mountain, you'd dig your way through it and find out everything you could about that mountain. So critical thinking is dissecting problems and determining are they all the details about a problem. Okay? All right. So that should take care of that. These are just learning objectives and such. Really, they're artifacts. You don't really need them. I probably should take them out of slideshows at some point. So, chemistry is going to be the study of matter and its changes. So everything we do involves chemistry. When you breathe, that's chemistry. When you eat something, that's chemistry. When you cook food, that is a type of chemistry. When you cook drugs, that's a type of chemistry. Hopefully you are not cooking drugs. So I hope you are not performing that chemistry. But those are all chemistry. So this shows you chemistry typically is the central science, the science that everything else tends to exchange through. So science is going to be the process of seeking an understanding of the underlying principles of nature. It's going to involve two facets to it. There's the technological facet. This would also be called the factual facet. This is the applied facet. Okay? And then there is the philosophical facet, or a theoretical facet, why things are happening, right? We explore the philosophy of nature, but we also explore the factual, concrete, making things happen of nature. So technology will be your direct application of knowledge to solve problems. Science actually grew out of natural philosophy, which is the philosophical speculation about nature. And so originally science grew out of the philosophical. We discovered enough of how things happen that it began snowballing into technology. And this has made your life incredibly different than it ever would have been before. For example, right now, the poorest person in the United States lives a standard of wealth that would be equivalent to a 8th century emperor. Okay, you have the aluminum stuff you have around you, the laminated stuff you have around you, the plastics you have around you. These things, if you brought that back 1,000 more years back, you would be as wealthy as an emperor. Your standard of living, for example, I'm 35 years old at this moment. I would be considered a village elder. I would be considered the oldest person that you could find in the surrounding villages, and I would be very, very, very old as of that day. I would be about the maximum age you'd expect somebody to live. 40 would be about the max. Uh, you guys would actually be considered middle age from about 300 years ago and back. So, yes, you 20 something, 20 ish year olds would be middle aged people 300 years ago. And the reason that everything has changed so much is the application of science in our lives, right? Specifically, the combination of the natural philosophy snowballing into technology, which snowballs into improving our lives. So, chemistry, this is going to be the discipline of science that deals with the behavior of matter. And remember, matter is all the stuff around you. So, it was the dream of Francis Bacon, who was a philosopher, that science would solve the world's problems and enrich human life with new inventions, thereby increasing happiness and prosperity. And yes, I understand that this dreams never always come to their fruition as purely dreams. There's also always another side to that. So, for example, Rachel Carson, this is a biologist, published Silent Spring in 1962. She proposed that the use of chemicals to control insects threatened the destruction of all life on Earth. And there has been some nightmare to the dream, of course. Science is, of course, a tool that we can use. Like all other tools, it can be used for good or evil. And I'm not going to get so much into the metaphysical aspect of this and the moral aspects of science. I want you to have those tools. I'm going to give you those tools. It is not my place to pass judgment on all good and evil in the world. That's simply not realistic. However, yes, every time you look at it, there is good and bad. However, the goods of science has made the lives and livelihood of billions of people possible. If we had this population before any scientific invention, we would all, about 3/4 of us would have to die right now, if you're curious. So, yeah. Oh, and another thing is if you actually got rid of all pesticides right now, went completely organic, as it is right now with the current technologies we have, you would have to kill off about 2/3 of all human beings so that you could feed them. So, yeah, it's not actually realistic to get rid of all pesticides. And yeah. So, green chemistry. This uses materials and processes that are intended to prevent or reduce pollution at its source. It's been a major drive over the last about 40 years in chemistry. Sustainable chemistry is designed to meet the needs of the present generation without compromising the needs of future generations. And this was a big focus for about 40 years now. This one's only been a major focus for about 30 so years. And really, the most work on this has been happening in about the last 20 years. However, the sustainable and green chemistry initiatives have gained amazing momentum over the last 20 years. There is actually 2 methods that were just developed this year and released that, if they can scale up, and they probably will be able to, might solve things like global warming. So, there is some major work being done. Science has 5 characteristics. Science is, most importantly of all, testable. Next is it's reproducible. If I can do it, then somebody on the other side of the world has to also be able to do it. It is explanatory, it is predictive, and it is tentative. So, one of the things I want to point out, explanatory, you have to be able to explain why that's happening to some degree. So, what your experiment you set up has to explain something. It can't just be a random experiment you do that you have no idea what's happening and you really don't know what's happening at all or doing or anything about it. You can't just throw stuff together and go, oh, that was neat, and then walk away, okay? That's not doing science. Predictive, ideally, when you go through the scientific method, you should give a prediction that you're testing, trying to disprove. And so if you cannot disprove it, your prediction will be upheld for that time period. You should again try to disprove it over and over, though. And that's one of the things that frustrates non-scientists about science is really science does not prove anything ever. What science does is we try to disprove everything, and then what we can't disprove, we go, okay, that's it for now. When we come up with something else, we'll try to disprove it again. All right. Tentative, you should never state, I believe this in science. That's not good science. So when you see people saying, I'm going to prove this, that's not tentative, that's bad science. Okay, it is not actually science. That's just very, very bad methodology. Scientific hypothesis. These must be testable explanations of observed data. These hypotheses are tested by designing and performing experiments. You notice that it keeps saying testable experiment. Test it, test it, test it. You have to be able to, and you must, test a hypothesis. This is one of the things I get very frustrated when they put supposed scientists up on these news programs and oftentimes even give them large amounts of government support is they propose hypothesis, they may even write books on it, and they don't test it at all. They're not actually scientists if you keep spouting hypotheses and you never give a method for testing them. One of the most famous ones of these is Hawking's. And he was a very good theoreticist, but he really wasn't a scientist. And the reason for that is he came up with lots of hypotheses. However, he never actually came up with methods of testing them. And he never tested anything. So he never actually made science progress at all. Now, some people use some of his work to progress science, which is good. That's great. I'm very glad about it. He was a brilliant mathematician, but he was not really a scientist when it comes down to it. As versus somebody like Albert Einstein, who, even though he never himself tested anything, he came up with experiments to do to test them. And then he would give those to other people and they would test them. And then that would confirm his hypothesis, i.e., he wasn't disproved by the experiment. All right, so scientific laws. Now you'll notice that scientific theory and scientific law are two different things. And this is one of the things that tends to confuse people a lot. So scientific laws summarize large amounts of scientific data and provide descriptions of natural phenomena. Notice you just are providing what happens. You don't tell why. That would be a theory. So some of the laws are things like the law of gravity, the law of conservation of mass and matter, and you also have the various gas laws like Boyle's law. So many of these scientific laws can actually be stated mathematically as well. And for example, Boyle's law has this mathematical statement right here, which is PV equals K. All this is stating is it's saying that pressure is related to volume. So you don't need to know this formula or anything. All this is demonstrating is scientific laws. So for example, the law of gravity. The law of gravity isn't something that we have to disprove anymore because you have proven it over and over and over every second of your life. So right now, you're fighting gravity to move around, right? You drop something and it drops to the ground because of the law of gravity. Gravity. Uh, Law of conservation of mass. You may notice that while you're watching this, you do not magically just disappear. The computer screen that you're watching this on does not magically disappear. That's because all mass is conserved. You don't magically not stop using power when you are watching this. It takes power to do it, right? And so, again, that's conservation of energy. Now, let me point out that our current perspective of the world, most people have a perspective of the world that's been framed by these scientific laws. For some perspective on your perspective, if you will, if you were to talk to somebody 500 years ago, they would literally think that you could open a closet and a goblin would pop out. That literally things popped into existence out of nothing. So, like, you could be sailing along the ocean and pop, there's a sea dragon. You could look in your pocket and pop, there's a gold coin. And, you know, if the gold coin wasn't there, then it wasn't like you lost it, it just ceased to exist. So, your gold coin that was in your pocket, it wasn't there, somebody didn't steal it, it just ceased to exist. Now, of course, we don't think like that because we're used to these scientific laws and our entire concept of the world around us is framed within those. So, yes, back in the day, they really did think, for example, that you could just be walking around and bam, gravity stops working and you fly off. That was really a thing at one point. And there's actually reports of people reporting these sort of things happening. Okay? Where literally they thought that somebody would have just drifted away and that's why they're gone. Or they just ceased to exist and that's why they're gone. So it's pretty crazy how much of our worldview is now actually based on scientific principles, which is probably good. A scientific theory, this is going to be a set of tested hypotheses that explain natural phenomena. Scientific theories are the best current explanations for natural phenomena. Theories are always tentative and may change as observations of nature change. So here's the big splitting points between scientists and non-scientists, or people that don't really understand science. Is scientific theories, these are many of the theories like the theory of evolution, which is the one that's very contentious, right? But these are also different things like the kinetic theory, okay? Or thermodynamic theory. Nobody really argues much about those because they're pretty well tested and people just don't really care much about them. But they're how you tell if things like thermodynamic theory is how you tell how efficient a car engine can get and what type of design for the engines would give you the best efficiency, okay? And yeah, they're very, very useful. There's a lot of information you can get from them, but most non-scientists never even bother looking into them and just don't care. Okay, so theories are something that has been tested repeatedly, but they are never facts, okay? Theories are always tentative. So this is what drives non-science understanding people nuts, is because scientists will put out a theory and then 30 years later it might change or completely disappear. We may have large theories that there's a great deal of use for them and they've been largely put out there and then we just get rid of them. We completely change the theory. And that's because somebody figured out a new way to test it. And they've tested it and it was wrong. Or at least a portion of it might have been wrong. And so we have to then amend our theory. And somebody that understands science, when they hear that a theory was proved wrong, they will go, awesome, amazing, that's great. Because that means a big breakthrough just happened. And every time a big breakthrough happens, lots of new technologies happen and typically people's lives get better. Now, a non-science, somebody that doesn't understand science, is going to go, oh, scientists don't know what the hell they're talking about because they got the damn theory wrong. That's the exact opposite. We know better now what we're talking about because we found out that theory was wrong. So we can now go on to a better theory. So it's almost the reverse of everything else in life, right? You want to prove it wrong, you want to be wrong, you want to be proven wrong. And that's because that's how science progresses forward. That's how it gets more and more understanding the world around us. So, unlike many other professors, I actually very much like people to send me parts where I'm wrong or, point out if I'm wrong on problems, that sort of thing. Because, number one, you were paying attention then. That's always a good thing. And number two, I like that discussion. I like that back and forth, proving things wrong. This is actually one point that almost everybody doesn't understand about scientific journals and what are called communications, which are the thin, small journal-like articles, but are not actually scientific publications. They're called communications. And that's that when a scientist publishes something, they're actually looking for people to test it and try to prove them wrong or explain what they couldn't understand from it. So the communications and publications in science, these are not completed facts. These are theories that they're putting forward and they're testing to try to disprove that theory. So scientific models, this is a form of scientific theory. These are going to be tangible items or pictures that are used to represent invisible processes. Many scientific models are simply something you could not see in your everyday life. And many theories actually are explanations, and that the reason for them not being laws is you just can't see them. So there is quite a large number of these that are very well documented, very well proven, but we just don't have the ability to see them all the time, so we can only take a small cross-section. And as you may have noticed, if you take a small cross-section, a small sampling of something, you can be wrong. You can be very wrong. Alright, so right here we see an example of this. This would be your water and your air molecules and how water vaporizes in the air. You don't need to know a huge amount about that yet. We'll go into more details. But we can't see this on a molecular level. And so this would be the kinetic molecular theory showing us how this would happen on a molecular level. Molecules are going to be groups of two or more atoms held together by chemical bonds. Now, atoms are the singular of the smallest denominator. They are the smallest you can get, simplest you can get, the elements. Okay? And those elements are, of course, carbon, nitrogen, hydrogen, the things you should see on the periodic table. I just, a while ago, saw somebody write, I can't remember if it was somewhere on the internet, I think, and somebody literally thought the elements in science and chemistry was fire, wind, water, and air. So please don't think that. They are the elements as in the elements on the periodic table, as in carbon, oxygen, nitrogen, hydrogen. Oh my goodness. Alright, so molecular models are three-dimensional representations of molecules. Science, this is limited to studying that which is observable as well as processes in which variables can be controlled. Notice all science is ultimately testable, observable. You can compare it and disprove it. Okay? If anybody says something like, I'm going to use science to prove/disprove God or aliens or whatever, that can't be tested, right? They're lying to you. They're trying to sell you a bill of goods. You can't use science to test something which cannot be tested, right? So anytime you hear that sort of stuff, that is just bullshit. They're screwing with you. Okay? It's not real. Say, no, you have nothing to do with science. Go away. All right. Science and technology, these are interrelated. They involve both risk and benefits. So the risk benefit analysis, this involves an estimation called the desirability quotient, DQ, which is actually just benefits over risks. It's something you typically do every day of your life. Should I jump out in front of this car so I can get over to the other building? No, because the benefits does not outweigh the risks, do they? All right. So for example, here are some different um, risk versus benefit analysis. So all causes, well, we all die of something, so everybody has a 100% rate of dying in this planet. Now, our likelihood of dying from cigarettes, for example, well, you have about 1 in 4 chance if you smoke cigarettes 1 pack a day. And so many people say that that is not a desirable benefit to risk analysis, and so they don't do it. Heart disease. So why do people exercise and watch their weight and do all these things? Well, much of it has to do with heart disease, right? And so you have about 1 in 5 chance of dying from heart disease, and so people try to curb that chance. All cancers, there we see those, and here we have a bunch of other ones. Now, why do people not worry too much about like a meteor coming down and hitting them in the head or lightning striking them? Because you have a very small chance, right, over your lifetime. Yeah, you probably don't want to go out during a lightning storm per se, but you're not going to have to stay indoors all the time because you just don't have a huge chance of dying from it. Airplanes are even less, so that's why people still fly in airplanes, despite the fact that every now and then they do, hit the ground in a negative manner. Anyways, terrorist attacks, you're very unlikely to actually be caught up in a terrorist attack. This is one of the reasons that people always point out that the terrorist scare is actually usually worse than the actual effects of terrorist attacks. Not that people haven't died from terrorist attacks, which is awful, but again, your chance of actually being one of those people is very low. All right, so right here we have chemistry as showing you sort of its central role. Now what you'll see is that these adjacent fields typically are interrelated closer, so you typically have more direct overlap between them. But if you go between two of these fields, you typically end up having to go through chemistry in some form. So for example, when you're looking at medicine versus archaeology or engineering, you're typically exchanging through some field of chemistry. Applied research. So most of the research you guys have probably heard about is called applied research. And this is going to involve studying a specific problem in an industry or environment and coming up with solutions to that problem. For example, one of the most prolific applied researchers of all time was George Washington Carver. And he did a huge variety of research with peanuts. And so in his research, he developed more than 300 products that come from peanuts. Various different peanut oil, peanut butter, and everything you can imagine involving peanuts. It's incredibly prolific research. And yes, by the way, that is a picture of George Washington Carver. And yes, he was a black scientist at a time that there was very, very few black scientists. So he's kind of an amazing individual. And if you've never heard of him, you really probably should look him up. He's one of those people that really is worth looking into. Kind of a cool individual. All right, basic research. This is going to involve the research for knowledge for its own sake. Oftentimes when you're talking about basic research, the findings in this basic research simply will not have a direct application you can put them to. You're not going to make something like peanut butter or oil to run a car or lube something. You're going to get an idea, an understanding of the world around you. So the findings for basic research may someday be applied to a specific problem in an industry or environment. And that's why basic research is typically funded by governments, and there are a few grants that are based on businesses. But the vast majority, about 90% nowadays, is funded by governments. And basic research oftentimes is the building block upon which you need to build everything else. For example, internet, computers, these all sprung directly out of basic research that then progressed on to a application nobody knew the use of, which then got you people figured out use for later. uh, so oftentimes the basic research are the major breakthroughs that will give you your applied research down the road. But when you first do the research, oftentimes you have no idea what it's going to get used for. You really just don't know what its uses could be because you won't really know what you get until you get it. Gertrude Elian's work with purines and their role in the cell is a great example of basic research. Nobody knew what the hell it could be for, but modern medicine now is largely, this is one of those key breakthroughs that has helped to create our modern medicine, our modern understanding of cell mechanics and the inside reactions and workings of a cell. Chemistry. This is the study of matter and its changes. Matter is anything that has mass and also volume. And this is kind of an important definition, by the way. So that is what matter is. It has mass and volume. So pretty much everything that surrounds you that isn't energy. Mass. This is the measure of the amount of matter in an object. You will notice that that is actually a circular definition. I've literally defined matter as mass and then mass back as matter. Yes, this is the most common definition you'll find. This is actually, it will work more or less for you. However, if you want a real definition for mass, mass is the inertia objects have or resistance to being moved. So for example, try this out. You have a lot less mass than the Earth. So if you tried to push the Earth, so take your leg, try to push it. Yeah, you really were trying to push it there, right? The Earth didn't move, did it? You moved. And that's because the Earth has a lot more mass than you do. And so the Earth has a great deal of resistance to being moved, whereas you have a lot less resistance to being moved. Now, when we talk about mass, an important factor in this, everything that has mass has some gravitational force. Yeah, gravity, as in you being pulled down to the Earth, that's gravity. The Earth has a very large amount of gravity compared to a human, and so that's the one we worry about when we're on Earth. Yes, as a body of mass, as a human that has mass, you do have your own gravity. Yes. It's just very, very, very small compared to something like the Earth. So weight is the measure of the gravitational force on the matter and an object. And so weight is actually gravitational force pulling that matter towards a body, like the Earth, or if we were on the moon, it would be the moon. And so the reason that this astronaut here looks like he's jumping around, he's not actually jumping. What's the problem is when he's on Earth, his motion to walk has a certain amount of push it needs to generate, right? And this force of the push is proportional to the force of the gravity of Earth. And so he's providing enough push to move his 180 usually. With all this equipment, he's probably somewhere in the 200 to 300 pound range. And when he provides that normal level of force on the moon has a lot less gravity. And so he weighs a fraction of what he would weigh on Earth. He weighs about a tenth of what he'd weigh on Earth. And so instead of weighing 200 something pounds, he probably weighs somewhere on the order of like 30 pounds. Okay? And so his normal push that he would do to walk will launch him into the air. Or her. It could be a her. I don't know. All right. Now, physical properties are those properties of a substance that can be observed without changing the substance. So some of the examples of physical properties would be things like their color. See, this looks like a nice metally color, copper. This right here is a nice purple color. And you get the idea. Those are color. You don't have to do any chemical change to observe them. You just look at it, cool, color. Mass, you can just weigh it out. You don't have to undergo any chemical change. It's a physical property. Weight, this is another physical property. These are some different physical properties of matter. We have things like okay. I didn't look at this table very well before I put it in here. There are actually a few things on this table that are chemical chemical properties. All right. Temperature. This is a physical property. So, for example, things like water boiling at 100 degrees Celsius, that would be a physical property of water. The mass of something, that's physical property. Color's physical property. I'm going to skip these real quick. Boiling point is a physical property. Hardness would also be a physical property. For example, iron is a lot harder than something like your skin, right? And so, again, those would be physical properties. The density would be physical properties. So why does wood float? Well, it's less dense than the water. Okay. Why does the metal sink? It's more dense than water. And water has a density of 1, by the way. 1 gram per milliliter. All right, now, taste and odor are actually chemical properties. To taste something, you're actually reacting that thing in your mouth, okay? And so that is a chemical property, actually. Odor, you react it in your nose, and in the back of your mouth, you have some, essentially what are smelling buds. And that's actually how you go through and figure out the odor of something. You literally react it in your nose. So that's also a chemical property as well. I gotta be careful about these damn tables, man. All right, chemical properties. Those are properties of a substance that can only be studied by forming new substances. So, for example, iron rusts, that's a chemical property. To figure out if iron rusts, you would literally have to rust it. Carbon burns. To figure out if carbon burns, you'd throw it into an oven and try to burn it, right? If it burns, it makes carbon dioxide. Bam. Now you know that's a chemical property. Great. All right. So those would be some examples of chemical properties. Those are actually examples of chemical properties. So that's fantastic. Now, physical properties and physical changes. These are interrelated. So physical changes are changes in which the chemical identity of a substance is not changed. So some of these examples would be you have water. You could freeze that water, it would still be water. So you don't change the chemical identity of that water. It's still water. You could melt that water. It's still water then. It's just liquid water. You could boil that water. And it's still water. It's just vapor now, right? Water vapor. And so those would all be examples of physical changes. Some more examples of those would be something like you could cut a piece of paper in half. That's still paper, right? You haven't changed its chemical identity. It didn't suddenly turn into gold. You've just changed its physical properties, its size. All right. Chemical change would also be similar to this. I'll do that in a little bit if I forgot to put this in here. So the classification of matter, you guys probably are familiar with these, but you've probably never thought about them in concrete terms. And so the 3 most important classifications of matter that I want you to understand and know are solid, which has a definite shape and volume. Liquid has a definite volume, but has no definite shape. That's why it takes on the shape of its container. A gas, this has neither definite volume nor definite shape. So if you release a gas, it's going to expand to fill the container, like a room, right? And it's not like it doesn't fill in the corner of the room, it will fill in the entire room because it doesn't have any definite shape. Okay, now this would be a great space to go ahead and mention that there's a weird phenomenon with science and chemistry and people trying to learn them. And that is, for some reason, everybody that tries to learn science, the majority of people that try to learn chemistry and take my class and try to learn chemistry, are they go, it is chemistry, and then they go, chemistry has to be hard, and then stop thinking completely and act like they don't know anything before this class existed. Okay? Literally just stop thinking. I will ask questions all the time on exams just to see if this is true or not. I've asked repeatedly in every exam for the last 4 years a question that goes something like, on a hot summer day, which of these would melt? And I get about usually a half of my class to 3/4 of my class that will answer me chalk. That chalk melts on a hot summer day. I mean, think about that. And the other answers are things like water and ice cubes, right? Ice cream. And they'll point out chalk and answer that. And that's because you oftentimes get so wrapped up into this being chemistry and oh my god, it's chemistry, that you forget you're living in chemistry. What everything around you is chemistry. And so, you knew all of this already. You're literally looking at it right now. You don't even need to know anything about it. You could just look at an object as a solid. Your desk, your chair, yourself, and go, okay, well, what do I know about this? It has a definite shape. It's not like it's just flowing, right? It's not like it's collapsing. It has a definite shape, and that's the shape of my desk, chair, or myself, right? It has a volume. It's not like I'm expanding out right now as I talk to you. It's not like my desk is expanding out as I talk to you or collapsing in. It has a definite volume, right? Liquids. Well, I have a liquid here in my cup. I'm drinking. And this liquid, well, it has a definite volume. It's not like it keeps expanding to fill out the entire room, right? Or I'd be wrecking my computer right now. However, it doesn't have any definite shape, and that's why it fills in my cup. It takes the shape of my cup. And so you already know all these things. If you don't know them, you can just look around you. So oftentimes people have problems and get problems wrong on these things, and really they shouldn't, right? You shouldn't. It's something you could just look at all the objects around you and know. So every time you get into a problem and you go, oh, I don't know if I know the answer to this, take a step back. Think about the objects in your world. Think about your life, okay? Does a gas have a definite shape? No. I release a gas in a room. It fills the whole room, and there's not like portions of a room it doesn't fill. It fills the whole thing. And so right here we see some of these different examples. Right here's a solid. This is what a solid looks like. The atoms in a solid are fixed in place, and they're very rigid. They don't move around a lot. A liquid, you break about 20% of those connections, and they start flowing past each other, but they're still very densely packed. A gas, on the other hand, they're spread out over space. They're moving all over the place, and they're not very densely packed. They're spread out, and they're not rigid at all. They're freely flowing completely. Okay, right here is how matter breaks down. So we have all of matter. It can be split into substances and mixtures. These are pure substance, and this is mixture. A pure substance can be split between elements and compounds. An element is only going to be one type of element. So we could have pure gold, we could have pure iron, we could have any of the elements on the periodic table. A compound, on the other hand, will have two or more elements. So, for example, pure water. Well, that's a pure compound, which is water, right? H2O. All right, so the other one on matter is mixtures. These are not going to have all one compound. They are not going to have all one substance. They're going to be a mixture between multiple substances. So two or more. We have homogeneous. Okay, you're gonna hear me constantly go back and forth on how I say these words. And the reason for that is I've been to a tremendous number of international conferences, and I've traveled a fair amount. Um, and so my accent has picked up a lot of different things. Now, there's two ways, major ways of saying this word right here: homogeneous and homogeneous. Homogeneous is the American way to say it. Homogeneous is the European way of saying it. Okay. Okay, so the other one over here is the American way of saying it. Excuse me while I try to readjust. Heterogeneous, or you can say it the European way, which is heterogeneous. Okay. Now, homogeneous or homogeneous is going to be where you can't tell the difference between the different components of the mixture by looking. Okay? It's going to be homo, which means same, throughout. So, for example, like 24 karat gold or 12 karat gold is going to be a homogeneous mixture. And that's because you can't tell the difference if you just look at it. Air around you, that's homogeneous. Coffee is typically a homogeneous mixture. Those are different versions of that. Right here, this is a heterogeneous mixture. And so if you look here, you can see little pieces of gold and water around them. A salad would typically be a heterogeneous mixture. Um, I don't know what else you'd be looking at because we're doing this online, but if you look at the Bethel desks, they typically have that sort of striped pattern. Those are heterogeneous mixtures. Um, your skin is a heterogeneous mixture because it has hair particles all throughout. You get the idea. Anyways, I think you probably get the idea. So elements, these are going to be composed of one type of atom, that is the elements from the periodic table of elements. Atoms will be the smallest particle of an element. They are the smallest designator you can have for an it still be a element. So these elements, they're represented by chemical symbols. Some examples of these will be C, small l, H, or Mg. And those will be things like chlorine, hydrogen, magnesium. Compounds. These are made of two or more elements chemically combined. Many of the compounds exist as groups of atoms bonded together as a unit. These units are called molecules when you have these groups of atoms combined into a single unit through bonds. A mixture is a physical blend of two or more substances. Notice that they won't be single compounds. They'll be different compounds or elements mixed together. So they have not chemically reacted, they have just been mixed. Homogeneous mixtures are going to be uniform in composition. Hetero, meaning different, heterogeneous mixtures are not uniform in composition. Right, so here's some of the different measurements of matter. So here is the type of physical quantity we're measuring. Here is the name of our unit that we'd be using. And right here is our symbol of our unit. So length is meters in the SI unit designation. And this is denoted by an M, lowercase m. And meter is, yes, a meter stick. That would be a meter, right? If you haven't seen one, honestly, I can't show you on the screen because it won't make any sense. So you're going to have to, it's about most people's shoulder, left shoulder, to the tip of the right hand would be somewhere around a meter. Okay? For me, it's actually closer to my left shoulder to my elbow because I have fairly wide shoulders. Now, the mass, this is the kilogram, and that's kg. Yes, that is kilo, as in I'm going to pay you 20K for a kilo of Coke. That is a kilogram of Coke, and the 20K is actually $20,000, which actually has to do with kilo as well, by the way. Hopefully you never say that sentence in an actual setting, though. Time, which would be second. And everybody knows seconds. Hopefully you know it. It's on the smallest hand on your watch that's moving really fast. All right, or your clock if you use your phone. Temperature. The SI unit for temperature is a unit that you probably have never heard before, and you've almost certainly never used before unless you've had a chemistry course before. And that is the Kelvin. Notice that it does not have any degree symbol because it is an absolute scale. And its designator is a large K, capital K. The amount of substance is actually the mole, and that's MOL for the symbol. The electrical current is an ampere, which is a capital A, and if you look on your charger, you'll actually find that unit, amps. And that's actually the amount of electricity that is going in at any one time. That's also the most dangerous of the designators for electricity, because if you have a full amps, you could kill yourself, actually. That's actually enough electricity to kill someone. You need 40 milliamps to start a heart. Luminous intensity, that's how much intensity, how much light a light bulb would be given off. Its unit is the candela. An interesting side note to this is the candela is literally the amount of light given off by a candle. Just one of those standardized candles. If you're curious, a meter is actually the shoulder width of an oxen. That's where that came from. So, kind of unique one. Right here, these are going to be the prefixes. So these are the numerical prefixes. In science, we oftentimes have to deal with extremely large or extremely small numbers. And so we're a little bit lazy. We don't like to write out things like 0.00000000001 seconds. And so what we do is we would write that we have 1 picosecond. And that would mean that we have 10 to the negative 12 seconds. We have something that's a very, very small amount of time. Okay, you actually are all familiar with some of these. And you may not have realized it. If you aren't familiar with them, then you really should look at your computer a little bit. Honestly, you're taking an online course, and if you don't know these, I feel kind of bad now. Anyways, so tera as in terabyte, that symbol is T, and that is 10 to the 12th bytes. Giga as in gigabyte, or gigawatt, which would be the amount of electricity several houses would use, like a neighborhood or a small town. Terawatts would be like the amount of energy, electricity that the whole world uses. Okay, all right. So a gigabyte would be 10 to the 9th, or a billion bytes. Megabyte, mega, would be 10 to the 6th bytes. That's how many bytes you'd have. Or, for example, megawatt, this would be the amount of electricity that a small, like, cul-de-sac sort of thing has. Or again, I'm sort of factoring in industry when I talk about these things, so excuse me if my numbers are a little weird for you to understand. Like a typical house usually uses kilowatts, if you're curious. Anyways, this would be 10 to the 6th watts would be a megawatt. Or 10 to the 6th bytes would be in 1 megabyte. And megabyte would be like the file size of a picture, right? A gigabyte would be a movie. A terabyte is a fairly good-sized hard drive. So most of you probably have like a terabyte hard drive. By the way, if you notice, these are each 1,000 times the next one. So this is 1,000 times giga. So there's 1,000 gigabytes in a terabyte. Or right here, there's 1,000 megabytes in a gigabyte. Or right here, there's 1,000 kilobytes in a megabyte. And yes, this right here is kilo, the same kilo that was kilogram, the same kilo that you're referring to when you talk about pay me 10K, that's kilo, 1,000. And so kilo is 1,000. Or another way of saying that is a kilogram has 1,000 grams in it. A kilobyte has 1,000 bytes in it. Hecto would be 10 to the second, that's 100. So a hectometer would be 100 meters in a hectometer. Deca, this has a K, so deca. This is 10. So a decameter would have 10 meters in it. Right here, this is deci, as in decimal. Its symbol is D, small d. So you would put a small d in front of your unit. For example, decimeter would be small d, small m. Now, deci, a decimal, or like decade, right? This would be 1/10. So there is 10 deciliters in 1 liter, or 10 decimeters in 1 meter. Now here, this is centi, as in like centipede, right? A centipede has 100 legs, and yes, centipedes do have 100 legs. I've been attacked by 3 of them in my life, and for some reason everybody always wants to know about me being attacked by centipedes, probably because of a little revenge for me giving you guys exams, huh? But yeah, so if you've ever seen a centipede, uh, 2 of the centipedes that attacked me were about 3 feet long, and about 2 something feet long. And then the third one that attacked me was a tiny one. That's the only one that actually managed to bite me, though. And I broke out in a huge rash when I got bitten by that small centipede. That was about 2 feet on each side on my leg. It was wrapped around my entire leg. It was really nasty. It hurt like hell. Anyways, when I got attacked by the large centipede, one of them actually managed to. What they do when they attack you is they wrap your limb with their body, dig their legs in, then their head goes in and puts its fangs in you, and they start pumping venom. Their venom is typically a paralyzing agent that can sometimes cause immune reactions. And that venom is strong enough to take down an elk, and then they would burrow inside of you and eat you from the inside while you're still alive. So they're very, very nasty. But the one that attacked me, I felt it pinch, and it wrapped my leg. When it was about to go with its head, I managed to grab it, rip it off me, and throw it, and then it managed to get up and run away. I've never successfully yet killed a fucking centipede. They're sons of bitches. They're just awful things. One of them I hit with a tennis racket. It got up and darted away, and it's just ridiculous. I still can't kill the fuckers. So I hate those things with a passion. Um, there's only one type of animal that I would be willing to just let's wipe all of them out of the earth, and that would be centipedes. Because they are mean sons of bitches. Anyways, that's a side note. Centi, as in centimeter, you all probably have heard of centimeter before. There's 100 centimeters in a meter, or another way of saying that is a 100th of a meter would be a single centimeter. Now, millimeters, you've all heard of those probably, or milliliters. Milli is 1/1000th. So there's 1,000 milliliters, or 1,000 milliliters in a liter, or there would be 1,000 millimeters in 1 meter. Okay, next one would be micro. I would like to point out that most of these, once you get very high or very low, they're simply going to be multiplications of 1,000. So each step will be 3 zeros or 1,000 times. So right here, these are times 1,000 each time, each of these big steps. Down here, it would be divided by 1,000 each time. Okay, so micro, you may have heard of things like microbiology or microbeads or microprocessors. These literally are denoting that they're in the scale of micrometers, that you measure what you're talking about. So the cells of in microbiology. would be measured in micrometers. And so there is 1 million micrometers in a meter. Or another way of saying that is 1 micrometer would be 1/1 millionth of a meter. Its unit right here, its symbol, is this looks like a U. This is actually called a Greek mu. Okay, if you're ever curious. All right, now nano. This is very small. This is where all those like nano product names and nano processor and nano beads and nano um, particles, that's where all those things come from. Or nanobots. They're all measured in nanometers. And that's where the nano from the names comes from. So nano here is 1/1 billionth. So a nanometer, there would be a billion nanometers in 1 meter. It's denoted by an N. So if you were doing this with meters, it would be nm. All right, now pico. Frankly speaking, you guys probably have never really encountered much that would be a pico anything. It's just a very, very small unit. It's not very common to hear about. And so, like picometers would be the scale that you'd be talking about a single atom. A nanometer would be the scale you'd be talking about like molecules and stuff. Okay? So picometers, that would be atomic scale. It's very small. That's 10 to the negative 12th. So there is 10 to the negative 12 meters per picometer, which would be PM. Femto. The only femto that I have ever really heard of in a sort of conversational-ish setting would be a femtosecond. And so the amount of time it takes for light to hit an object in front of you, like let's say your computer screen, and then bounce back to you would be somewhere on the order of a femtosecond. Okay? It would be measured in femtoseconds. And so a femtosecond would be 10 to the negative 15 seconds in a single femtosecond. Or another way of saying that is there would be 10 to the 15th, positive 15, femtoseconds in 1 second. And it would be denoted by an FS, femtoseconds. All right, now these right here are the prefixes. You may wonder what use these are. First off, it's amazingly how often you will actually hear these prefixes if you know them. So if you know these prefixes, you can then pick up where people will use them to sell products, to name products, to do lots of different things. And if you know what these prefixes are, you can sort of say, oh, that's bullshit. So if you see something that's not made in a laboratory setting, there's no nano anything about it, okay? They're just selling you nano. They're using it as like a word to make it sound sciencey, okay? If it's made in a more scientific setting, like where they make CPUs, computers, then maybe, yeah, it might actually be nano. Okay? But most times, nano's just sort of something they say. And the other thing, and this may not apply to you for now, but maybe someday it will, is these are the sort of things you need to understand if you're going to understand medications people give you. One of the things is I teach a lot of nursing chemistry, and I've used to teach like 900 a semester when I was back at UMKC, Kansas City area. Now I only teach probably about 30-ish, 40-ish a semester, but still. And I've had about at least a dozen nurses come to me after I teach them their prefixes and say something on the order of, I didn't think I'd use that. I didn't think I'd really care about my prefixes. But then I actually ended up saving this patient's life, or I helped out this patient because I knew my prefixes and I kept mistakes from happening. And the last one, the one that really sticks in my mind at least, is a nurse that was just starting her job. The doctor note wasn't very legible. And so the nurse that was training her was going to give a patient milligrams of medicine because the notes looked like it said mg. And the one that had been trained by me went, that doesn't look exactly like an M. That could be micro. And if we give the person 1,000 times the amount of medication, they're going to die. We better go back and check with that doctor. And they went back and checked with the doctor. The doctor went, yes, that was micrograms, and you need to give them their medication in micrograms. And they gave the patient the medication. The patient did not die, which is good. If they would have given the patient micrograms, it would have been 1,000 times the dose, and that patient would have died. And so she was like, yeah, I'm really glad I actually paid attention. I saved that person's life. I was very happy. And she was very smiling big, and that was a good accomplishment. I mean, she saved somebody's life on one of her first days. I was very happy for her. Anyways, I get stories like that every now and then. So, prefixes, yes, they are kind of boring. Yes, you do actually see them all over your life if you actually pay attention. But they are also very useful, actually. Now, here's the different types of measurements. We have mass. The SI unit of mass, like I said before, is kilogram. Now you can know that kilo is actually the prefix. The base unit here is gram. Length, the unit for that is meter. Now the SI unit for volume, this is one of the places where this is very different from the metric system. And so the SI unit for volume is actually meter cubed. Time, the SI unit for time is the second, which is pretty much the same as any other unit, which is nice. So when you hear nano, you should think nanometer. So for example, nanotechnology is the study of manipulating matter at the atomic or molecular level. And this would be measured in nanometers. And right here we actually see a graphene tube, which is, you can do a variety of kind of cool applications with. Some of them are you can make structures that are stronger than steel, but are actually very cheap and easy to make. Anyways, density, this is defined as the amount of matter in a given amount of space. And so density will be mass over volume. Typically the units for density would be grams per milliliter or grams per cubic centimeter. Now, milliliter, cubic centimeter, and centimeter cubed, these are all the same thing. They're all the same unit. So when you hear milliliter, you should also think cc. Or if you hear cc, you should think milliliter or cubic centimeter or centimeter cubed, right? They're the exact same thing. So right here, this is the density of copper, which is 8.94 grams per cc. Now, you will notice that actually, if something is greater than 1 gram per milliliter, which is the density of water, it will sink in water. If something's less than the density of water, it will float. Okay, so many people at this point, when I talk about density, and I mention this, tend to typically ask me, Dr. Clausen, is that why boats float? Kind of. So, for example, you float in water when you fill up your lungs because your density actually goes to less than the density of water, 1. When your lungs are deflated, many people will actually be then denser than water, and so they'll start sinking. However, some people are not, depending on the amount of fat to bone to muscle ratios. All right, now, like a wood branch is going to float in water because its density is less than the density of water, okay? And a hot air balloon is going to rise in the sky because its density is less than the density of air. Yes, those are true. When you have something like a boat, though, that isn't completely enclosed, it's a little bit more complicated. Essentially, they use a little trick, which is the surface area of the boat, right? Making the surface area that the boat occupies on the top of the water act like it has a density that's less than water, okay? It's similar, but it's not quite the same thing. If you want to talk more about it, you can send me a message and we can go back and forth a little bit, okay? But it's a bit more complicated. So when you calculate the density of a metal sample with a mass of 18.96 grams and a volume of 4.31 centimeters cubed, what do? Well, let me first give you good problem solving skills, okay? And when I say good problem solving, I mean all problems in life. So, good problem solving says you always should go ahead and list out what do you have, what do you need, how do you get there, okay? That's just good problem solving for anything. It could be your goals in life, it could be a math problem, it could be anything, okay? So, that's a great life skill. All right, now I have mass, right? I have this mass right here. I have this volume here. So I have grams and centimeters cubed. What do I need? Well, I need density. Density is grams over centimeters cubed. So that's all I have to do. I have to take grams, I have to divide it by my centimeters cubed right here. So I take my grams, I divide it by centimeters cubed, and I'm going to get my density right there. Energy. This is the ability to change matter, either physically or chemically. One of the things I want you to keep in mind is energy and matter are never ever created nor destroyed. They are only changed. So energy is going to exist in two major forms. We have potential energy. This is stored energy. This is energy not currently in use. This is the energy something has for being saying set up on your desk. If you knocked it off, that would convert to kinetic energy. This would be the energy an explosive has before it detonates. This is the energy being stored in your battery. Okay, so kinetic energy, this is the energy in motion. So when you're using your phone, you're having some degree of kinetic energy, which is actually the energy of the electrons moving in your phone, if you're curious. And could be even if you have like a fan in your phone, or if you really use your phone a lot, you could end up with other forms of kinetic energy too, which would be things like heat. Or for example, you have something sitting on your desk. It has potential energy. When you knock it off the desk, that will transform into kinetic energy. And that's when it's falling and that hits the ground. Heat. This is energy that is transferred from hotter objects to cooler objects. So heat energy is the energy that's being transferred from a hotter object to a cooler object. And that's how heat always flows, right? From hot to cold. Temperature. This is the average kinetic energy of the atoms or molecules that make up an object. And so I want you to envision something moving through space. So one object moving through space, right? And we can very easily calculate the amount of kinetic energy of that object. It has a certain amount of kinetic energy. If it hits you, it'll transfer some of that kinetic energy to you, right? But what happens if you have billions of objects, trillions of objects, all moving in different directions and all moving with different speeds? Well, you can't really calculate kinetic energy for that anymore. It's just too damn complex. And so what you do is you get temperature. That's how you measure then randomized kinetic energy going in all different directions. Okay? And so that's how you measure the kinetic energy of a bunch of atoms and molecules. Temperature. And when you're measuring heat, well, all heat is transfer of kinetic energy from things that are moving fast and bouncing around a lot to something that's moving slower and bouncing around less. Something hot is going to have a lot of randomized kinetic energy, bouncing around a lot. Something cool is going to have very little randomized kinetic energy. And so you have the stuff that's bouncing around a lot causing the stuff that touches that was slower before to get accelerated by getting knocked into. Okay? Think of it a bit like if I had one side of the room that was very active, then I put that room that's very bouncing around all over the place with the room there where everybody's sitting down, well, the people that are sitting down are going to get knocked out of their chairs, right? And they're going to end up getting bounced around. So the units of heat. Heat energy is often measured in calories or joules. This calorie right here that you're seeing, the small c, this is different than the calories on the back of a package, okay? And I'll tell you how they're related in just a bit. But first, let me get the definition out. So 1 calorie, which is the small c, cal, is the amount of heat required to change the temperature of 1 gram of water 1 degree Celsius up. And so it would literally be the amount of energy you need to take 1 gram of water and raise it 1 degree Celsius. All right, so a calorie is going to be 4.184 joules. And joules is denoted by a large J. And right here would be your conversion factor. Okay, now, how is a calorie and the calorie you see on the back of packaging for food related? You'll notice that the calorie on the back of packages of food is a large C, a capital C. And so the calorie on the back of a package of food is 1,000 calories. Okay? Small c calories. So it's just because the amount of energy in food is a lot larger than what you need to heat up 1 gram of water, which is a very small amount of water. And so you take 1,000 times this number. So it's 1,000 of these small c calories. That would be a calorie that you'd see in the back of a package of food, this large c calorie. By the way, another name for a large c calorie would be a kilocalorie, because it would be the kilocalorie, 1,000 times. So again, right there you see your C, large C, capitalized calorie. Yes, that would be a kilocalorie. Right here we see our temperature scales. And so here we see Fahrenheit, which all of you are probably relatively used to. You will notice that we freeze water at 32 degrees Fahrenheit and we boil water at 212 degrees Fahrenheit. This doesn't really make as much sense as the Celsius scale. Celsius scale is very nice. I very much like that one. And the reason for that is 0 degrees Celsius, you freeze water. 100 degrees Celsius is the boiling point of water. And so if you ever need to relate these, 1 degree Celsius, 100 degrees Celsius is the same as 180 degrees Fahrenheit. Now, these degrees Fahrenheit, degrees Celsius, what you'll notice is the reason these are degrees is that they have zeros that do not actually correspond to no energy, to no temperature. The zeros in Celsius and Fahrenheit are a relative measurement. They just, literally a scientist came along, the person that invented these scales, and said, I'm going to make the 0 degrees Celsius freezing point of water. There you go. And so it is a relative scale from the freezing point of water. Now, Kelvin never has degrees, and that's because Kelvin has an actual 0 point. 0 Kelvin is absolute zero, meaning there is no heat energy at all, meaning all of the molecules and atoms are frozen in space. That is 0 Kelvin. You can't get slower than 0 Kelvin, which means everything's frozen in space. Okay? All right, so this is the conversion between Kelvin and degrees Celsius. So if you have degrees Celsius, you add 273.15, and that will give you Kelvin. So the human body temperature is 37 degrees Celsius. If we convert this to Kelvin, we would take 37 degrees Celsius plus 273.15, and that would give you 310 Kelvin. Okay, so you can test the validity of a claim by using the Flares test. Now, let me point out again, a number of these problems, whenever we're doing these different problems, we're trying to think about these things, you're going to notice that I oftentimes point out how they were come up with or factors about them. Part of that is I'm trying to give you how you can think to come up with conclusions. I'm trying to actually expand your ability to critically think, okay? You really shouldn't just be sitting there and letting what I say seep into your head. That's how you're going to get yourself made into a parrot, which is not good. What you really want to do is try to make connections yourself. Try to synthesize this information into ideas, okay? And that's going to improve your critical thinking. All right, so let's examine basic critical thinking abilities and validating claims. So flares represents falsibility, logic, replicability, and sufficiency. So if you pass a claim through all four of the flares tests, then it may be true. However, that doesn't guarantee it's true. It just tries to eliminate stuff that's false. If it fails even one of these tests, then it's very likely to be false. So let's go ahead and go through each of these points. We have falsibility. Do we know any of the facts that were provided, were they false? Can you prove any of them false? If somebody tells you you fall upwards, well, fall. Test it, right? See if it's right. Logic. Okay, now logic is probably the weak point of the flares test, honestly. Logic is extremely hard to actually accurately apply. And the reason for this is that, honestly, most people simply have not worked out their logical thinking well enough to truly apply it evenly. Okay? It's something you could literally get a degree in, and you would still not be a total master of it. And then, on top of that, people try to bend logic into pretzels. It's very, very hard to accurately apply logic. Anyways, logic would be things like, I don't want to use a political, let me try to think a little bit. I keep pulling political things for logic. Let me go ahead and go the other ones and see if I can come up with a logic one that's not political, because people get very angry when they talk about political logic things. And almost every politician is just fails the logic test horribly. Anyways, replicability. Can you replicate it? So if somebody tells you that every time I flip my hand, there's a quarter in it, can you do it? Try it? Nope. Okay, well, it's not replicable. So obviously that's not right. They're doing something else. They didn't tell you. Sufficiency. Does it sufficiently... Okay, sufficiency. Sorry about that. I need to get a drink. Do they have sufficient number of tests to even draw a conclusion? So I took a poll and I found out that, everybody supports murder. Everybody supports murder. I tested 10 people. They were all on death row. They were psychos, but, they all supported murder. Does that make sense? No, I don't have enough people to even begin to draw a conclusion, right? And then my people I chose are just bizarre, right? It doesn't make any sense. And so this is actually one of the problems with most of the polls you see on the media is they don't tell you what the number of people they tested and where they tested those people. So yeah, they could take a poll. They take a poll of 100 people in some suburb of LA. That's not going to represent the rest of the country. Or some suburb of Kentucky, right? Again, doesn't represent the rest of the country. You don't have them scattered out. So it's just not sufficient, is it? Another part of sufficiency that people oftentimes forget to take into account is there actually a sufficient amount of something to think about this? So, for example, people come on and claim that they are experts in something. Have they actually spent a sufficient amount? Oh, I wrote one book, so I'm an expert. No, writing one book doesn't make you an expert. Writing 10 books might make you an expert. I have 30 publications in my field, 2 book chapters, 4 lawsuits, and I still can't say that I'm sufficient enough to be an expert in every aspect. Now, am I sufficient enough to be an expert in infrared spectroscopy and molecular structure? Yeah, yeah, because I have quite a bit of material behind me, right? Okay, so logic, let me see if I can give you a decent example now. Let me pause this to get a drink while I'm at it. Okay, so logic, you should try to logically chain through a series of thoughts to draw your own conclusion for that and test if it violates logic. Be careful though for false analogies, which is what most people will use to essentially bend logic to their purpose. Okay? So, for example, I could say, because my grandfather smoked his entire life and never once got cancer, you obviously do not get cancer from smoking. And so you would then go, well, that's a false dichotomy for logic because I can list off hundreds of thousands of other people who have gotten cancer and it is directly correlated with smoking. Um, Frankly, if you want examples of people misusing logic or failing the logic test, uh, if you actually go through all of the logic chains and consequences, um, just look at any news program. It's sad, but it is true. It's really bad, and because we're getting close to election right now, it's incredibly bad. So, if you want bad logic, go ahead and look there. Uh, be careful with logic, though. You can very easily logic yourself into convincing yourself of very strange things. Okay? Um, there's sort of a saying that I was once told, and it really rings true. The smarter you are, the more you can logic yourself into a pretzel. You should always test your logic. Okay? Let me give that warning. Anyways, this is good critical thinking um, fodder. Okay? Take what I've given you, try to think through it, see if you can come to other different evaluations of it or a different way of looking at this, dissect what we just talked about, and synthesize your own opinions. And then, what I would highly recommend is you talk those opinions out with other people who have synthesized their own opinions so that you can test each other's understanding of something like a Flair's test, logic, falsibility, replicability, sufficiency, what these mean, how you can use them to disprove things. This is how you critically think, and this is how you get yourself better at critical thinking. Okay? And this is how you make your brain a true marvel rather than wasted space. All right? You have a great day, and I'll probably be putting out another video Thursday. Have a wonderful day, have a wonderful week, and stay safe.